Hi there, Andrew Dunkley here. Thanks for joining us on Space Nuts Q&A. And on this episode, we've got a few things we need to talk about. Terraforming, for starters. We get questions about terraforming fairly regularly, but we've got a new one. We've also got a question about a protostar. Fred will love the name of this, L1527. We'll see if we can answer that one. We've got a question about the enjoyment of science fiction. Are there limits to what you can do that will make or break it? And a couple of our younger listeners have chimed in with questions as well. We'll deal with all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And with me again is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. Looking forward to a few Q&As.
Yes, we've got quite a bit to get through. A couple of these will be pretty quick because one of the questions, which is almost ironic, asks us exactly about something we spoke about last week in episode 401. So we'll be able to make a reference to that. But let's begin. Well, actually, let's deal with that straight away. A young listener named Oliver, 11 years old from Queensland, has sent in a question and said, I was just wondering if there was any chance that Titan could have microorganisms. And, well, up until recently, we might have said yes. And I think the chance still exists, but some recent data has been put together that suggests Titan probably not as life-worthy as we once thought, Fred.
That's right. So the bottom line from our discussion last week was that the calculations that have been made by some astrobiologists demonstrate that the water that filters down through the icy surface of Titan won't contain enough of the carbon-containing material that we know is on the surface of Titan to make any difference to the ocean underneath. In fact, it was 1 elephant mass per year, was it, that was filtering down 7.5 tons. And that's a tiny amount when you compare it with a water reservoir that has, I believe we said, 12 times the amount of water as the Earth's oceans have. So people are a bit depressed about that. I think I mentioned in the program, I'm more optimistic because there is a possibility that there might be microorganisms that don't use water as their working fluid, but use liquid ethane and methane as their working fluid, and they will be very different from what we know on Earth, but microorganisms nevertheless. So I think there's still a possibility, Andrew. I'm not as pessimistic as maybe the authors of that article were.
Yes. So there you go, Oliver. The new data, which is based on modelling, so they don't have absolute proof, but it does suggest that if certain things happen the way we think they did, Titan's less likely to have life as we know it, but it might have other forms of life. But I wouldn't write it off completely. But it also kind of puts a bit of tips water on the other ice moons having life as well, because they're less likely than Titan, apparently, to harbour life. So, Oliver, thanks for the question. But if you go back to episode 401, there's a much broader explanation of the situation you've asked us about. Next question comes from Dan. Hi, Andrew and Fred. I know a few listeners have touched on this before, but I'd like to go a little further on the terraforming thing, if I may. What would happen if we were to place a huge megastructure at Venus's L1 point, something like a vast solar panel that blocked all the light from the sun? How long would it take Venus to cool down, and would that eventually lead to the runaway greenhouse effect collapsing? It comes from Dan in California. I've got a nickname for Dan in California. I'm going to call him Caladan, which is one of the planets in a sci-fi show that I've watched recently. Couldn't help myself.
There you go, Andrew. Yes, so this touches on things we were talking about last week as well, because we were talking about flotillas of tiny spacecraft to reduce the radiation from the sun on Earth. And the idea was to do exactly as Dan suggests, put these flotillas of spacecraft at the L1 point between Earth and the sun. So if you did the same thing with Venus, it turns out that a solid lump of something, like a big sunshade, even if you could build something which would have to be the diameter of Venus to work at all, that will be unstable. It's not something that would probably stay intact. The gravitational forces might well break it up. Right. So you're better off starting off with small things rather than big things. Dan's question's not about that, though, really. It's about if you did switch off the sun as far as Venus is concerned, how long does it take to come back to something that we might recognise as a planet like Earth? And I honestly don't know the answer to that, but my guess is we are talking about geological timescales. We're talking about millions of years rather than a fortnight or something like that, just because that sudden loss of energy would certainly transform the climate. It would shock the climate into a change, but how long it might take for the change to take place, I don't know. Yeah. Just thinking slightly laterally, though, the thinking, I believe, as far as a kind of quasi-related event on Earth's history, which is the Chicxulub impact 66 million years ago, I think scientists who look at that, so yes, that thing ejected huge amounts of dust into the atmosphere, which blocked off the sun. And I think it wasn't a fortnight, but I think the lengths of times for things to recover were measured in decades rather than millions of years. But with Earth, what you're talking about is a temporary blanket of the sun, which is all the dust in the atmosphere. That eventually falls out and the sun comes back to its original brilliance. The atmosphere regains its original transparency. And so you're returning to the status quo, whereas with Venus, you're fundamentally changing everything. If you leave that sunshade in place, or equivalently fill the atmosphere with dust, that might have other consequences, though, because dust retains heat. So I think it's going to take a lot longer.
Yeah, indeed. Yeah, we've talked. This was quite a while ago. We talked about that. I mean, Venus is an example of a planet that may at one time in its past been Earth-like, as was Mars, and so we've got 3 planets that at one stage during the life of the solar system were Earth-like, had more what we would consider normal terrain and normal conditions, for want of a better word.
Yeah, and at some time in its past, the Earth was more Titan-like because there was the snowball Earth era when everything was frozen. So yes, it's gone through various climatic changes and events. Fortunately, it's landed up where it is at the moment in terms of the Earth's, ambient temperature, 15 degrees Celsius on average.
And rising.
And rising, yes, that's right.
All right, Caladan, thank you so much for your question. Always like to get those kinds of questions and dice them up, but probably not feasible in terms of building the structure, and timeframes would be rather extensive, and I'm probably understating that. From Dan in California to Dan in Brisbane, who wants to talk about a protostar, Fred.
Hello, this is Dan from Brisbane. If you do a Google search on protostar L1527, you'll see an amazing James Webb Space Telescope image of a accretion disk with 2 cones of material being ejected above and below the accretion disk. Now, I believe this was the same situation as what happened to our solar system when it was forming, but this protostar is 100,000 years old, where our star is 4.6 billion years. So I'm wondering, did similar clouds of material form above and below the accretion disk plane? If so, what happened to them after 4.6 billion years. I believe that there's two forces of pressure coming from our sun. One is the photonic pressure, which I think would be spherical, and the other one is the solar wind, which probably varies over time, but I think it would probably be spherical as well. So I'd like to know, how does the pressure, say, on clouds of gas compare from, say, the solar wind and the photonic pressure? And also, what has happened to this cloud of material above and below the plane of our solar system? Is there any remnant of it left?
Okay, thank you, Dan. A lot of information required to answer that one. I did look up the website that he referred to, the NASA website with that image of L1527. And I can see what he's saying. I think we did talk about something like this recently with the hourglass image that is created by that effect. Well, I'll leave. It's yours, Fred. Passing the ball. How do you answer this one?
So Dan's conjectures are right. It's actually not really an accretion disk. It's a protoplanetary disk that is in orbit around the star itself. Although, as the caption that NASA provides for that Webb telescope images suggests, the cloud of material is actually feeding. It's basically the nebula within which this star has been born is feeding the growth of that protostar. So it's a process that probably is includes various examples of stellar burps, if I can put it that way, what you'd call in a more formal sense sporadic ejections, where material is actually ejected from the star as it's forming. And indeed, there's evidence for several past stellar ejections in the Webb telescope image. It's a really extraordinary image, and thanks to Dan for drawing our attention to it. But to bring it more up to date, so it's a long time since I've looked at these, but my understanding, if I remember correctly from my time when I used to study stellar evolution, is that all sun-like stars go through what's called a T Tauri phase. Now, T Tauri is basically another type of star. I'm just going to Google that as well, just to get my bearings correct with what I'm talking about. I spent, in fact, I think I have a paper back in my long ago history where I was talking about T Tauri stars, because I worked on them with a colleague on an instrument I just built. So T Tauri stars are a class of variable stars that are less than about 10 billion years old. They're named after the prototype T Tauri, a young star in the Taurus star formation region. They're found near molecular clouds and identified by their optical variability and strong chromospheric lines. So they are basically sun-like stars that have not yet become sunlight, typically less than 3 times the mass of the sun. And what they do is they basically emit winds. The sorts of winds that they blow are like the solar wind, but much stronger and with much more energy associated with them. So T Tauri stars are effectively how a newborn star in a nebula blows away the residual gas, gets rid of all this stuff that has formed its cocoon for a few, perhaps tens or hundreds of millions of years. So they are, they're basically embedded in these gas clouds, but they blow out these winds, which I think, as Dan surmises, are probably isotropic. That means in all directions, spherically symmetrical. So check out T Tauri stars, Dan, and you'll find that might be the mechanism by which the residual gas and dust is blown away, and so that an object like the sun, who's already lost its siblings, the sun would have been born with other stars in the same dust cloud, and we can't identify what those stars are. They won't be far away, and I'm sure it will happen one day that stars with identical chemical composition to the sun will be discovered. But that means that because of the T Tauri phenomenon, we've lost all those remnants of the cloud, which is so obvious in the picture of L1527.
Okay, there you go, Dan. If you do a search for T Tauri, it's T, single letter, and Tauri, Tauri, T Tauri star, if you want to read up on it. And thanks for the question. It was a really good one. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go. Space Nuts.
Let's go to another question, and this one comes from Star. So we're talking about a protostar. Now we've got a question from Star. I just wanted to start off by saying thank you so much for this amazing weekly podcast, twice a week now. I always look forward to it every Thursday, and your episodes help me get through my astrochemistry homework. Oh, okay, good. I hope you didn't get all your answers wrong based on what we've said. I was wondering, when it comes to sci-fi, does your enjoyment of it depend upon how scientifically accurate it is where applicable, or does it not matter? Also, if you have a favourite sci-fi series, book, movie, etc., I would love to hear about it. From Star. My enjoyment of sci-fi is not limited to anything. I will take every story on its merits, whether it's feasible or not. I suppose one of my favourite sci-fi movies would have to, in recent times, be The Martian, which did actually base a lot of its storylines on feasibility. They did stretch the envelope a bit, though, didn't they, Fred? A couple of times there with certain things. Yeah. But they basically went with this could be possible scenario. But then I look at a movie like Passengers, which is absolutely and utterly not feasible, because you're basically cryogenically freezing people and stopping their lives so that they can travel 90 years to another world and then suddenly start their lives again. So they're 90 years older without getting any older. And a lot of things in that film were just, they were stretching it beyond reasonable possibility in terms of the story, but a great story nonetheless, and I really enjoyed it. And as far as my favourite sci-fi story of all time, I'd have to say it's Dune. I think Dune is probably one of the best sci-fis ever written, but there are so many. It's probably unfair just to name one. I mean, Isaac Asimov's Nemesis is brilliant. Hitchhiker's Guide to the Galaxy, probably one of the greatest of all time. The list goes on. There's 3 that I can think of: Parallax, the Turanian Enigma, the Hitler Paradox. They're all really good too.
They're familiar sounding titles.
Yeah, they are, don't they? Yeah, a bit of an unknown author, that bloke, but great ideas, just not a great execution. Fred, you're not so much into sci-fi as I am, are you?
No, I'm not, definitely. And that comes from, the
real thing.
Well, I don't know that it's that. I used to read huge amounts of sci-fi when I was just a lad, but these days there seems to be far more to do, and so it's not so much. But just picking up on what you said about Passengers, was it? With that idea of suspended animation, that, in my experience, goes back to 1955 when Frank Hampson, who was the author of Dan Dare in the Eagle comic in Britain, actually put the whole crew into suspended animation for about 10 years, so they could get to the solar system of Los with its 2 warring planets, Kryptos and Phantos. That's for me was the stuff of why I became a scientist, actually, because I was totally immersed in all that stuff back in the day. I have to say, though, and in fact, actually, Frank Hampson, who was a genius artist as well as a great educator and a great feminist as well back in the day, he had a character called Professor Jocelyn Peabody, and she was the one who explained all the science. And so he put, the scientific explanations for what was going on in the mouth of a woman, which was very unusual back at that time, but fantastic stuff, way ahead of his time.
Yeah.
But maybe it was that. Maybe it was the effect of my all-time favorite movie, 2001: A Space Odyssey, where you are actually keeping within the bounds of scientific reality. That, to me, is an added. If a science fiction story keeps the physics right and the biology right, then it strikes a chord with me. Compared with the ones that don't, and they're just annoying.
Yes,
to a scientist.
Gravity comes to mind. Gravity was just way beyond the realms of.
Gravity was good in the sense that
it was entertaining.
The basic premise of a kind of Kessler syndrome thing was good, but the idea of being able to walk from one space station to another with your pressure suit on, that's just not on. And the other one, Interstellar, was, I think, loved it. A bit over the top in that regard, in stretching the relativistic ideas. Yeah. The one I liked, I've forgotten, we've talked about it recently. What was the one called that had an interpreter working out how to communicate with Arrival?
Arrival.
Yeah, Arrival.
Magical movie.
I like that one because there was so much that could be real in it rather than, being scientifically fictitious.
That is assuming that giant squid-like creatures did come to Earth.
Of course, that's right. You've got to have that to start with. But the point is, you can't eliminate that scientifically because they might well be there.
That's very true.
Just don't know. That's the thing about aliens. You're never going to be able to prove that they're not there.
That's right.
You can prove they're there if you find one, but you can't ever prove they're not.
Yeah. So you started something there, Star. So, but the truth for me is it doesn't matter whether there's a reality potential in it or it's just gone way to the extreme. I love the ones that are based on real science, but Hitchhiker's Guide to the Galaxy, which is based on nothing but a man's incredible imagination,
that's good stuff,
just nails it for me. Does. Thanks for the question. That was really good. Quick one, Fred, to finish off from 9-year-old Ted, whose father has sent the question in on his behalf. Joe, why can I sometimes see the moon during the day in the UK? And does that mean there isn't a moon in the sky on the other side of the Earth? Thanks, Joe and Ted. The reason you can sometimes see the UK in the sky is because the pollution's blown away briefly.
The moon in the UK sky, yeah, that's right.
Or the cloud.
Or the cloud. Well, it's true. That's absolutely true. The fact is, you can see the moon during the day anywhere. It's not, because the moon, as it goes around the Earth, is very often above the horizon at the same time as the sun is, and its phases are different. What you tend not to see is a full moon during the day, because that tends to be all night long. You might see it at dusk and dawn, but you won't see it in a full moon in the middle of the day. Whereas you can easily see half moons in the middle of the day and all the rest of it. And that doesn't matter where you are, UK, North Pole, South Pole, Australia, anywhere. But you're right. If you see the moon in the day during the UK's daytime, you won't see the moon in the sky in Australia, because we're basically on the other side of the planet.
Almost exact opposites, yeah.
That's right. We're almost exact opposites. So,
so that's why, there are times, though, because of the positioning and the distance, you can see the moon from a great many places around the world at the same time. I've sometimes been watching live golf from the United States, and they'll have an image of the moon, and I'll be going, I can see that too. Yeah. And, I'm thousands and thousands of kilometres away, but it's all a matter of the angular perspective, isn't it?
Yeah, it's pretty easy, actually. Anywhere on the same hemisphere that's facing the moon will see the moon. So that's half the Earth.
Yes.
So it does include the Pacific Ocean's big, separating Australia and the United States, but they can be simultaneously in the same hemisphere pointing towards the moon. So you'd see them. Yeah.
There you go, Ted. Hopefully that answers your question. And keep on gazing at the sky. You just never know what you might see. It's always fun up there. Fred, that brings us to the end. And if you do have a question for us, please go to our website and send it to us on the AMA tab or the little button on the right that says send us your questions. We'd love to hear from you, whether it's in text form or audio form. And don't forget to tell us who you are and where you're from. And don't forget to subscribe if you're a YouTube follower. And have a look around on the website. Some great sci-fi books on there and some great science books as well.
Even better.
With more credibility. Thank you, Fred. A pleasure as always.
And for me too, Andrew. Thank you for putting up with my ramblings, and we'll speak again soon.
We will indeed, and they're not ramblings by any means. Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks to you in the studio for being just a nice guy. Oh, I said something nice. And from me, Andrew Dunkley, thanks for your company. Looking forward to catching up with you again later this week on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.